Hello everybody, my name is Creus and I'm a student of the degree in Data Science and Engineering in the Politècnica University of Catalonia in Spain, and I will now present this research work where I have worked together with Professor Silverio Martínez and Xavier Franch, and that we have called Integration of Convolutional Neural Networks in Mobile Applications. We basically study the problematic of the deployment operation of these deep learning models into environments with limited computational resources, and we do so by means of a practical study where we develop a variety of convolutional neural networks and we integrate these in a simple application to perform traffic sign recognition. So I'll start by making a quick review of what is the most common tendency when using deep learning models in mobile applications, and that is the one that requests its usage to a server, and it is actually this server the one that is storing the complex model, and it just computes the results, obtains the predictions, and sends them back to the end user by means of an internet connection. So that is actually a feasible solution since we can exploit very complex models, since we're making use of the high computational resources in the server, and that also implies a low computational cost in the mobile environment, and it all works in real time thanks to these internet connections. But that is also the drawback of this solution, since we are assuming that we have internet both for hosting the server and for the end user connections, and that is an assumption that may not always hold. So that is not actually the solution that deploys the deep learning component into the mobile application, since we're just making use of it. So from now on, we'll work over this viewpoint of the deep learning based software lifecycle, where we distinguish between these four phases that are iterative and cyclic, and that deal with the data management, that go with the modeling part of the deep learning components, and then with the development of the applications or the environment that will integrate these components, and finally the operation of these systems. So from this viewpoint, we established these two research questions where we study the challenges of the creation and integration of these complex CNNs into deep learning based mobile applications, and also we study what are the criteria needed in order to reason about the trade-off between accuracy and complexity of these deep learning models in mobile applications. So notice that we do not only study the deep learning deployment operation, but we do so in an end-to-end approach of the life cycle, since we can find these challenges or these optimizations wherever during the deep learning based software lifecycle. So this is how our practical study looks like. It follows the same schema of the life cycle. So starting from the left, we see that we deal with traffic sign data and that we model 5 different convolutional architectures. Top 3 here are handcrafted CNNs, and last 2 are pre-trained and downloaded from PyTorch. Then we develop 2 applications that integrate 2 of these 5 models, and finally we operate with these applications in the operation environment, and we give answers to our research questions. So starting from the left, our work in the data management phase is actually minimal, since we make use of this benchmark dataset that is called this German traffic sign recognition dataset, and that contains images that do look like this. And what we try to do here is train the convolutional models to classify traffic sign instances within this data, and then we try to make them generalize in the operation environment, and in our case we do this in the streets of Barcelona. So now we summarize the performance of the models in the modeling phase. On the left, we see their storage weight as a representative of the complexity. Here, the storage weight is also directly proportional to the number of parameters that these models have. And on the right, we see the accuracy that they achieve on the test split of the German traffic sign dataset. So from this summary, what we realize is that the small CNN is the most promising one of our handcrafted CNNs. It only weighs 22 megabytes and achieves this very high accuracy that is around 95%. We also realized that the mobile net architecture might be the most promising one, since it is the lowest weighted one and achieves almost the highest accuracy. And finally, we realized that the ResNet34 is the one that is solving the problem at a higher accuracy. So from all these, the 2 models that we will be deploying to the applications will be the small CNN for our handcrafted CNNs and the ResNet34 for the pre-trained models. So regarding our development phase, what we do is building the deep learning components with the PyTorch software over the Kaggle GPUs, And then we develop the applications using Unity, the Unity graphical engine, and we make them work over the Android operating system. So a very key and central part here is this ONNX file format, which is the one that allows us to export the trained models from PyTorch into some kind of serialized or compressed versions of this. And thanks to a very recent library in Unity that is called Unity Barracuda, we are able to import the models in this file format and just make use of these in the operation application. So basically, we built a very simple application that makes use of the device integrated camera, and we want the end user to be able to take images of traffic sign instances and then see the results that the models obtain in their recognition in real time, if it is possible. So now we summarize the system operation phase, where we see on the left the input image that we are taking and feeding to the model. And we can realize that in a first iteration, the ResNet34 is actually capable of generalizing its knowledge, and we see here that it is able of offering correct classifications and at a high level of confidence. And we also see that it does not happen the same with the small CNN that is not actually very capable of classifying correctly. So remember that the two models achieved a very high and very similar accuracy in the modeling phase, but only the ResNet is here capable of classifying correctly with the operation data. So what we do in a second iteration is collecting all the images that we took in the first one, and that consists of a bunch of 200 images, and we annotate these images and we feed them to the models again. So we update these models and we integrate them again into the application. So what we obtain with this data augmentation technique is actually a pretty noticeable boost in the performance of the models. Here we see now for the same traffic sign instance, the small CNN offer a correct classification and at a confidence of a 99.99%, which had never seen before here in the applications. And also the indicators of confidence of the ResNet34 have been sharpened here. So pretty impressive results here. And actually, we see that for the ResNet34, we obtain a very robust and consistent performance, where it is even able to classify these very complicated input examples where we're actually feeding two traffic signs in the same image. So here we summarize this performance within the two iterations of the operation phase, and we realize that what we have done actually is getting the accuracies that the models achieved closer to the real ones that they achieved in the training data set. So we here evaluate the performance within the two iterations. So now we have made it to the point where we can give answers to our research questions, and the first research question regarded the challenges of the deployment of deep learning-based software, and the first challenge regarded the frameworks and their poor availability, and the fact that they are in a very early first stage. So we verify this challenge, and we do so at the moment that we could not deploy the mobile nets architecture into the applications, just because this architecture contained an operation that is very common in PyTorch, but was not yet supported in the ONNX file format, and nor in the Unity Barracuda library. So just because of a very silly incompatibility, we were not able to deploy this mobile net architecture that is actually designed for being deployed in mobile applications. So what we do, apart from verifying this challenge, is uncovering a new one that we call software dependencies, where we basically state that we see two strong separating line here between the development-sided environments and the operation-sided ones, where a developer will basically must assume that it will need to combine two different technologies for building deep learning-based software. And what this implies is a new list of challenges that regard the correct classification, correct combination, of these technologies, also the design of two identical preprocessing pipelines, one for each software, and the support or the adaptation of the export and import operations within these two technologies. So regarding the second challenge, that was the data software dependency one, we strongly verify this one as we obtain a very high volatility in the performance of the models when they are fed different data. And what we do for solving this one is focusing on solving the fourth one that was about the sustainability of the models. So we make the systems more, the applications more sustainable thanks to this data augmentation technique that we commented before. And what we actually achieved by making these systems more sustainable with the data augmentation technique was actually smoothing this dependency in the performance between the data that was being fed to the models and the environment where we were using the application. So this is why we show this as a kind of a loop that it is solving itself, since the data augmentation technique is making these systems more sustainable and smoothing this dependency at the same time. So finally, regarding the explainability challenge, what we do in our practical study is providing these very simple indicators of confidence that are just probabilities of class memberships, scaled up to percentages. And we see, for example, in this image here, that we're not actually perceiving the uncertainty of the input images in the models, since the ideal answer here would be that the model told us that it is not seeing any traffic sign here, right? So what we do here is just providing these very simple indicators of confidence to offer a very simple level of explainability to the user, and we verify the need of the presence of any level of explainability to the user in this type of software, but we do not consider this challenge of a major concern, since it might not generalize to the majority of the applications of deep learning-based software. So regarding the second research question, that was about the trade-off between the performance trade-off, which takes into account the accuracy and the complexity. What we do is motivate many points of future work that regards the support of more export and conversion operations, just like the ONNX file format, since it has become a kind of bottleneck nowadays in this deep learning-based software pipeline. We also motivate further development of the frameworks that support the development of this life cycle, just like it happened to us with the mobile nets architecture, that it contains operations that are not yet supported. And we finally motivate this design of more optimized architectures, just like the mobile nets, as we state that this provides a very noticeable increase in the performance in the environments with limited computational resources. So another thing that we state regarding this trade-off is that the deployment operation of deep learning models actually collides with the benefits of the transfer learning. So we know in transfer learning that training these very generic networks in large amounts of data and then transferring the knowledge of these generic networks into to solve specific tasks actually provides state-of-the-art results in many cases. And this specific task could be traffic sign recognition, for example. But what we state is that it collides with the deployment operation collides with this transfer learning methodology, since these generic networks are usually of massive weight and very complex, and these are just designed to achieve these state-of-the-art results and are never thought to be deployed into environments with limited computational resources, just like mobile applications. So finally, we discuss a possible implementation of our deep learning-based software, and in our case, the application could consist of the integration of the two models, like the small CNN and the ResNet that we commented, and we would give the user the option to use the small CNN as a default one, since it achieves a very similar accuracy in both environments as the ResNet34, and it is less complex, so it works better in real time, and it has less memory cost and storage weight. And if the user was not satisfied with the results that it is obtaining with the small CNN, we would give it the option to switch to the ResNet34 in order to obtain these more robust results. So this has been everything for my part. Thank you very much for having me, and I will now be open to answer any questions. Thank you.
Hi, very good day to everyone. So we are back to the discussion section, and this one is for the second paper of this session, Integration of Convolutional Neural Networks in Mobile Applications. So we have a couple of questions on the chat. If you have more questions, please just write them on the chat. So the first question by Per is, you show a huge difference in the storage weights between models. Is there any difference in the computational power required? We are fortunate to have all the authors here with us, Taj.
Sure. So there definitely is, since it is true that we plot the storage weight to represent the complexity of the models. But I would like to indicate that this storage weight is strictly related to the number of parameters that these models have. So in terms of computational power, the power increases as the forward operation through the network, as we pass the data through the network, the fact that there are more number of parameters makes this operation more costly. So indeed, the big CNNs that we showed require a more costly operation in terms of computational power than the small ones.
Yes, yeah, thank you, Roger, for the answer. And then I'll continue with the question from Luis. I think it's related also. Did you explore differences in terms of the energy efficiency? So how do you think developers can address energy efficiency constraints?
So that is a good point, because we did a quantitative analysis for the accuracy, for example, of these models when achieved, when developed in the applications, and also of this complexity that we measured with the storage weight of these models. But then when we tried these applications and we had our mobile devices in our hands, we just evaluated in terms of qualitative analysis, for example, the real-time performance of these systems, or the fact that the battery cost, right? The fact that the device was using its battery at a higher speed. And sure, that is also, as I was mentioning before, linked to the complexity and to the storage weight of these models. But sure, there is it is a very interesting point to provide quantitative analysis on the energy efficiency that can be measured, as you ask, for example, with the speed in which the battery is being spent, or also with the real-time performance that these models offer in the mobile devices.
Yes, thank you, Roger, for the answer. And I think we still have time for one more question. Then there is a question from Per. Must this computation always take place in the mobile, or can they be computed in the network or on the edge?
So what we study particularly is the fact that these operations are being computed in the model, but this model is fully being integrated into the application. So we want to clearly distinguish between the the AI-enabled systems that make use of external computers or servers for performing these operations, and we want to focus on nowadays, with this big hardware revolution that we have, and big models also, how is this constrained by the fact that the operations related to AI have to be computed in the same device that is the one that integrates the model. So, for example, this has the capability of not depending on these external computers, has the capability of not depending on, for example, internet connections or other connections to these external devices, right? So we evaluate only the performance when these operations are being done inside the mobile device.
Yes, thank you for the answer. Yes, I think we only have like 45 seconds left. Maybe my question is generic one. What's the future work that you're planning to do next?
So we want to provide more quantitative analysis on the operational environment, and not only like the accuracy or complexity when we were developing those models, but also it would be great to like annotate quantitatively what's the dependence on this real-time performance of the systems, or these generalization capabilities when deployed in the mobile applications, and not when being modeled in our computers.
Yes, thank you very much, Roger, for the answer. So we still have a discussion room. So please join the authors to join the discussion room, and thank the author again for a very nice presentation.